Good evening, everybody. Welcome to our institute here, the Center for Astrophysics. All three of us are on the Kepler team, so we, of course, upset that Kepler is no longer functioning as we hoped it would. But we have a lot to do, and we are still working actively on its data. I'm going to tell you about results past, although very recent. But stay tuned because we'll have many more things to talk to you about as time passes. So how many of you saw already the Hollywood movie Gravity? No, not that many. Not many. So you know now that the Hubble was destroyed in that movie. But did I give out? It's in the first 5 minutes of the movie, so I'm not giving out.
Spoiling it.
Yeah. But really, Hubble is fine. Hubble is working, and actually is going to help us catch up with some of the work that we still have a backlog from Kepler. It is Kepler that, unfortunately, is not working as well as we would like to. And so, Hubble is the telescope that brought you the fantastic images of space, the pillars of creation, as they're called now, star-forming regions, to the very distant edge of the universe, as we can see it now, the most distant galaxies here into Hubble ultra-deep field, to the beautiful images of planetary nebula, which are in fact old stars as opposed to planets, beautiful, amazing dying stars, and stars which are in large groups like these globular clusters, stars that have just blown up like this beautiful image, or places where stars are just born, like the Orion star-forming region with the Horsehead Nebula. And this is all from Hubble, which is a space telescope just like Kepler. Kepler is a space telescope that you've heard about and we're also excited about, that brings to you something a lot more subtle, but it brings a breakthrough in human science that happens only once in a century, maybe even once in 5 centuries. And we are living in it. That breakthrough is happening as we speak today. What is it? What Kepler is telling us is that the majority of the stars out there that you see tonight and that we see with Hubble or any other telescope seem to have planets. And a huge fraction of those stars with planetary systems have in their planetary system a habitable planet. Are they inhabited? That's the big question. And that is indeed where we want to go next. And so when we talk after Kepler, what we want to tell you is how Kepler has helped us and is still helping us to go to that next step, which is to find out if there is life on other planets. And so let's talk a little bit about Kepler still. The reason I don't have a nice, beautiful picture like that I have of Hubble is because Kepler is not in orbit around the Earth, like Hubble is. Kepler is actually far behind the Earth on an orbit around the Sun, about 20 to 30 moon orbits away in the back of our planet. We wanted to make sure that Kepler can stare in an uninterrupted fashion in this direction towards the constellations of Cygnus and Vega without any interruptions, looking just in that part of the sky with very high precision. You can see this large Kepler field, as we call it tonight. In fact, we'll make sure to point you in that direction to the western part of the horizon where the Kepler field is. So what Kepler does, it stares at a large number of stars there and looks for stars that are dimming slightly in their brightness and do so in a periodic fashion. So what that is in the little insert here, the tiny eclipses, or as we call them, transits of the planets orbiting their stars. So that's how Kepler helps us discover planetary candidates. And we have more than 3,000 of those already discovered. And then we have to do a lot more work to turn those planetary candidates into real validated, confirmed planets. But we already know some of the main aspects of what Kepler was supposed to give us, which is the statistics. What is the fraction of Earth-sized planets that is orbiting solar-type stars? The reason Kepler no longer can continue doing that, although it completed 4 years of collecting data, is because in this part of the spacecraft down here, those gyroscopes that David just told you about, which are about that big, and it has 4, one spare, but 2 of them stopped working, so that's why it cannot point as accurately in that direction of space anymore, because with 2 you can only point in 2-dimensional space, and the 3rd dimension keeps sliding away from you. So let's start with the seemingly boring part, but I would argue this is the breakthrough in human science that we're living through right now. That's the statistics. And that can be represented as of January of this year in terms of a histogram of the types of planetary candidates and planets that Kepler has discovered so far. Starting with Jupiter's and even larger than Jupiter planets, and all the way down to Earth size. This is the bar here for Earth-sized planets. So you see a lot of numbers here, but the most important numbers to see here is that, first of all, we have a lot of planets. So the statistics is good and sound. We have a lot more planets in the smaller sizes, and particularly here in the Neptune size. And then we have quite a few in Earth size and super Earth size. You would say, well, we understand why this number is rising, and that's actually good news. We have a lot of small planets. You may be disappointed that then it's dropping down, but don't worry about it. The reason these numbers are dropping down is because Kepler, even Kepler with its precision, has a lot more difficulty discovering the small planets compared to the bigger ones. So what you see here is Mother Nature. Mother Nature makes less big planets than small planets. What you see here is the limitations of human science. We cannot yet do as good job at discovering the big planets as we do the small ones. But we understand that distribution in terms of fraction. And so if I turn now this into fractions, and now we'll refer to the work of one of our own, Francois Fressin here, but again, the Kepler team, you see this going up. And again, this is still incompleteness, but the small planets are definitely there. So we can confidently say that there are many small planets in that range of radius, and that more than 40% of stars have at least one of those small planets with orbits smaller than that. But the more important thing is when you ask, well, what about the smallest stars which have small planets? Not the stars like the Sun, but the smaller stars. Because there, the habitable zone is closer to the star. So maybe we can say something about habitable planets. And indeed, the answer is yes. If you select 95 planet candidates, which are all those points here that you see on this diagram, which shows you the size of the planet again. This is the Earth size, 1. And gives you the light received by the planet relative to Earth. The Earth receives 1. At 1 Earth radius, 1. These are hotter, 10 times, 100 times more light. Ooh, that's very hot. That's terribly hot. These couple of ones are less than 10 times, maybe 5, 6 times. It's pretty cold out here, but these 3 ones in the green zone are the ones which would correspond to the habitable zone, as we call it, the region of orbits that are not too hot, these are hot here, not too cold, just right for liquid water to be on the surface. So if you take those 95 planet candidates discovered so far from the Kepler mission, you find 3 right in the habitable zone. It's very exciting. That's work by some people right here. And remember that name, Dressing. That name is Courtney Dressing. And make sure next month you come to hear her to tell you all about that, because you will hear from the person who discovered that one of the most important discoveries this year. She will tell you how important and what exactly happened here. All I want you to take out from this is the big number. That is what she did, and you'll find out more next month, is telling you that totally as a total in the galaxy, there are more than 200 million habitable planets. And that means something very important, which Courtney is going to explain to you next time, that if you look closer to us here, closer to the solar system, you will discover at least 300 and maybe more of those habitable planets right in our neighborhood. So then we can do something about it. And this is where I want to take you next. The next step is to find out if there is something interesting going on those planets, not just the statistics. What is it that these planets are like? What is it that the conditions are on the surfaces? And is it possible that we have a fighting chance to discover life on them? Kepler is giving us some clues on that as well. And what we hope now with the numbers that Courtney found with Kepler is that we'll be able to do this in the next 10 or so years, within our lifetimes. And one way in which we understand that this could work is by looking at another of Kepler's discovery, one which our team here was very much involved in, and we announced in April this spring. It is the system which is called Kepler 62, and which consists of 5 planets orbiting a star which is slightly smaller than the sun, but still, very similar to the sun overall. 3 of the planets are pretty close to the star. You can see them in the actual comparison with their orbits. And 2 of the 5 planets, number 4 and number 5, are further away. They're in a region which is also shown here in green, which, as you know already, is called the Habitable Zone. The first one of the 2, number 4, is this one here, which seems to be a little bit warm, so probably very cloudy, like Venus. The second one, number 5, is on the outskirts of the habitable zone. It's probably a little bit chilly with some snow and ice here and there, but still in the habitable zone. So there should be some liquid water in somewhere on the surface of that planet. So we have here 2 planets, similar in size to the Earth, which are in the habitable zone, in a system of 5 planets, which is Kepler 62, which we can study. We can study them because Kepler allows you to measure very precisely not only their orbits and know that they're in the habitable zone, but also their sizes. There they are. Very precise sizes. This is all to scale. Planets and orbits are to scale, as it says here. There is the Earth, and you can see they're slightly bigger than the Earth. And you can immediately see as well that if they orbit a star, Kepler 62, which is slightly smaller and less luminous than our own sun, the habitable zone happens to be closer in than the habitable zone on a bigger star, like in our solar system. So the orbital periods are more like 8 months, 7 months, and 9 months, as opposed to 12 months, like for the Earth. But that puts them right in the habitable zone. They're very interesting planets because, judging from the distribution of the 5 planets' sizes and densities in 62, E and F, given that we know their sizes very precisely, are most likely a type of planet which we call super-Earths, which we don't have in our solar system. They're slightly bigger than the Earth, yet they're solid planets, but with a large amount of water in them. So we call them water worlds, just so that you know what I mean by this here. Quite often the Earth is called a water world, but if you take all the water that we know of on the surface of the Earth and in the interior of the Earth, all the water that we know of the Earth, it will be this little marble here, shown in the just above Dallas, Texas. If you think about a water planet, a water super-Earth, that is a truly planet made mostly, or at least to a great extent by mass of water. So you have a planet which is totally covered with water, an endless ocean if it's in the habitable zone, and hence the surface, it's at a clement room temperature, so the water is liquid. Very unusual type of planet. We don't have anything like this in our solar system. So with my colleague Lisa Kautenegger here and graduate student Sarah Ruckheimer, we set to explore what water super Earths in the habitable zone would look like if we could do some remote sensing of them. And we hope to do remote sensing of some of these planets, although for Kepler, they're usually pretty far away. So we call this spectra, but even if you don't really want to go into the details, this is how these planets would look in the infrared. And we think the warmer one, Kepler 62e, will be a water-dominated atmosphere. That is, will be a very humid, kind of warmish, not very pleasant kind of atmosphere. So you have a lot of water that you see there. The colder one, 62f, should be a carbon dioxide-dominated atmosphere, all said and done, with carbon dioxide prominently showing there. There's still water, of course. And if they happen to be warm and rocky, just like the Earth, then the Earth looks like that. So what I want you to take out from this is two things. First of all, we can tell the differences between different types of planets in the habitable zone if we could take this kind of data for them. And as you will hear from my colleague, we actually know how to do this, as amazing as it may seem to you. The second thing which I want you to take from this is that some of these features, which stick out here as sore thumbs, are very particular, and we put them on purpose here. This is ozone, and this is oxygen. You don't expect to see ozone and free oxygen in an atmosphere like that unless there is something green and slimy in the water. As we know here on Earth, these are cyanobacteria, which are producing oxygen gas. This is how the Earth atmosphere was enriched in oxygen. So when you think about how are we astronomers even talking about searching for life on other planets, well, you know our entire roadmap. We're finding the planets, we find the planets which are potentially habitable, we get them as close as we could to us, and with the big telescopes, we're looking for biosignatures, gases that could be produced by life on them, and we compare and match and say, okay, so this is a gas that shouldn't be there because it will disperse very quickly if it was produced in non-biological ways. So there must be something going on which keeps pumping into the atmosphere. And for that, you need to do a lot of things. And Kepler was the first step, doing the kind of discovery which led to 62. Kepler 62 is another step. You have to validate the planet, you have to confirm it, you have to try to measure the masses of those planets because you have to know what their mean densities are. And then one day, as you will hear from my colleagues, you can go to the next step and say, okay, now I know how to go and look for those biomarkers like oxygen gas. And Kepler has now finished collecting this precision data that we've received for 4 years. But in that data, there is still a lot of planets and planetary candidates that need to have all this work done. And this is where we are going next. And we'll be working on that for the coming few years. In fact, we just inaugurated a year ago a new spectrograph on the Canary Islands, which is the most precise such instrument for following up on Kepler targets. And we are already on our way, and stay tuned for some of the most recent discoveries still coming from Kepler, because Kepler provided the data which we then take and make use of by observing it with this spectrograph. So you can see me there holding on to it, but it's actually completely sealed, so nobody can go in there now. So this is just to introduce Kepler to you and why after Kepler is such an exciting time, because all of these most important discoveries that we built Kepler for are going to come in the next couple of years. And they are going to help us to then leap to the next step, which my colleague David Latham is going to tell you about, and which is really important for our search for life. But before that, there is a very important part of that science that Kepler is doing, which my colleague Soren Meibom is going to tell you right away. So without revealing what that is, Soren, it's your turn.
Thanks.
You want to be at the beginning,
Yes.
not the end. Come on, keep it. How do you get to the beginning?
I don't know. Why is it not showing up? The
Well, you start talking, I'll get it. Don't want to show the.
is it somehow?
I don't see how to get it. Okay, you.
Go to number one, number one here.
Yep.
Okay, and then play. All right. Can you hear me? Okay, so some of it is working. Good. Hey, thanks for coming. In the spring of 2009, Kepler launched. NASA launched the Kepler mission, and they launched the Kepler spacecraft, this fantastic, successfully mission, into a heliocentric orbit, where Kepler is trailing behind the Earth around the Sun, as Dimitar mentioned to you. And from this orbit, Kepler has been able to stare continuously in the same direction at a little patch of sky in the constellation of Cygnus. Now, the primary goal of the Kepler mission was to observe isolated stars like our Sun or smaller in this little patch of sky, about 160, 170,000 of them, to look for the dimming of their lights as a planet would transit across them. Okay? And Kepler was exceptionally successful in doing so. However, what I'm going to talk to you about today is motivated by the fact that in the Kepler field of view, there are four special astronomical objects called star clusters. And these gravitationally bound collections of stars, and you see an image of one up here, motivated a special study as an integral part of the Kepler mission called the Kepler cluster study. Now, over the next 15 minutes or so, I will present to you results from part of the Kepler cluster study, the part that focuses on searching for planets around stars inside of star clusters. Star clusters are valuable astronomical objects because we can more easily determine the properties of stars in star clusters than we can for stars outside of star clusters, the so-called field stars, the ones that Kepler have mostly been looking at. And so we can also more easily determine the properties of their planets. See, the properties of a planet are connected to the properties of the stars. But star clusters also allows us something extra exciting, and that is to study the effect of the stellar environment, the stellar neighborhood, so to speak, on the formation and evolution and survival of planets and planetary systems. And so, to understand that better, we need to understand a few things. We need to understand a few things about the formation of stars and planets. Oh. Do you want less sound? I want a lot less sound. So, I want just my sound. So the point to make here is that planets formed around stars, okay, like little sidekicks fighting amongst each other in their infancy to grow fastest and to find a place in a stable orbit around the star. And this process takes time, millions of years in fact. and it's thought to be rather delicate, as microscopic grains of dust have to grow from millimeter and centimeter sized pebbles to kilometer sized planetesimals, and eventually into planets. And it's easy to imagine ways in which this process can be disturbed, perturbed, perhaps even halted. So that's the first thing we should appreciate. The next thing I want you to appreciate is that it is in fact very rare that a star forms in isolation. Most stars, as you are seeing in an animation here, forms together in groups or clusters, where a large cloud of dust and gas in our galaxy will be perturbed and so gravitationally unstable, start fragmenting, and rather than forming one star, you form thousands of stars that are bound by their mutual gravity into a star cluster. And this is what you're seeing in animation here. So thousands of stars forming together. That's the formation of a star cluster. And that is the more common way in which stars form. In fact, despite its current single status, there are evidence to suggest that our sun formed in a cluster with perhaps more than 500 stars or so. Now, most of these groups or clusters, just like the sun's childhood cluster, fall apart. They have too few stars to withstand the internal and external dynamical stresses that they are exposed to. And so they are simply scattered, they fall apart within a few 100 million years. And as stars leave these clusters, as these clusters dissolve, they join the general field of stars, what we call field stars, with their planets. And it's around such isolated field stars that Kepler have been so successful in finding planets. And we estimate that about half of them, maybe more, when we get better instruments, will have planets. Okay? But the interesting part here are the less than 5% of clusters that survive to become older than a few 100 million years, billions of years old. Those clusters survive by virtue of being very rich in stars and very dense, so they can withstand the stresses that are imposed on them in the galaxy. And so they represent an extreme amongst clusters on the distribution of cluster properties. They're much richer and much denser in stars. And so they represent an environment, okay, a neighborhood that is much more extreme than the environment or the neighborhood of our own sun or all the other isolated field stars that we find planets around. So we don't know to which degree this environment affects the formation and evolution and survival of planetary systems. But if we go and look for planets in clusters, we can try to measure what is the frequency. Are there planets in there? How frequent are they? What is the nature of planets in clusters? And we can learn what effect does the environment, the neighborhood, have on forming planets. And so this is what we've been trying to do with Kepler. Let me briefly explain to you why is it an issue? Why do we think that it's an issue to be a planet trying to form in a cluster? If you have a rich cluster, like the ones that get old enough that we're looking at with Kepler, that survive for billions of years, you form a lot of very massive stars as well. We call them O and B stars. They have masses from 3 times the mass of the Sun to 30 times the mass of the Sun. Those are very massive hot stars. And they emit a lot of light in the ultraviolet and the extreme ultraviolet. Such ultraviolet and extreme ultraviolet light can heat and evaporate the material in these disks around neighboring stars. And the winds from them can drive this material away. This picture here tries to visualize that. And so it's thought that these massive stars can in fact influence these protoplanetary disks around neighboring stars. And within certain danger zones, it's called, they might even be able to strip these neighboring stars of their planet-forming materials. So if you have a rich cluster with such massive stars, that might affect your ability to form planets around the neighboring stars. The other point to make is that these big guys, they end their lives within a few million years in very powerful supernova explosions, uncomfortably close to their neighbors trying to form planets, right? So what you see in this little animation here over to the left is a cluster of about 6,000 stars. And every white flash you see is one of those big guys, O and B stars, going supernova over the first 10, 20 million years. So this is the kind of environment you have to imagine that we have to form planets, clumping together dust of grains in stable orbits until we finally have a planetary system. So that is the reason why we have asked ourselves, what is the effect of the environment on forming planets? Even beyond the lifetime and lives and deaths of these big stars, there are other issues too. When you have that many stars together, you have what we call stellar encounters. Passages so close by stars that their mutual gravity can affect them and their companions. And the more stars you have, of course, the more encounters you will have. In fact, the number of rate of encounters goes as the number of stars to the second power. So in rich clusters, you expect to have many more close encounters that can perturb. When you have stars coming that close together, within a few times the extent of a protoplanetary disk, for example, or within the few times the orbital size of a planet, that can perturb the system, make the system unstable, may perhaps prevent formation or eject planets from the orbits around neighboring stars. So for all of those reasons, it's very reasonable to ask the question, or to expect that perhaps the frequency or nature of planets and planetary systems in clusters is different than around the isolated field stars, the stars that didn't grow up in this kind of an extreme environment. So this is, of course, not a new question. People have been looking in over many years, as you can see in this list here, to try to find planets in clusters. And they have so far been unsuccessful, primarily because they didn't have Kepler available. They were simply limited by their sensitivity to what Dimitar told you are now the most frequent planets, the small planets. They couldn't find them because a small planet dims less light than a big planet when it goes in front of the star. The other limitation to all of these surveys was that the larger planets, the ones that they could actually find in their data, were much less frequent, as Kepler has also demonstrated. Right? So despite the fact that none of these surveys found any planets, we could still not say anything about whether planets were more or less frequent in star clusters than outside of star clusters. Now there are other ways of finding planets. You perhaps heard about the Doppler technique, or when you look at the reflex motion of the star, the wobble of the star as the planet goes around. That technique is not dependent on seeing a transit. And so improvements in this technique have led to detections of 4 large Jupiter or larger sized planets inside star clusters. And from those results, we've been able to say that at least the frequency of giant planets like Jupiter inside of clusters is not inconsistent with what we see around isolated field stars. So that is the first step toward finding out what effect does the environment have. What effect does it have to mean to be in a cluster on the frequency of planets? So back to Kepler. These are the 4 clusters within the Kepler field, from 500 million years old to 1 billion, 2.5 billion years old, and 8 billion. So the clusters in the Kepler field, they range in ages over the whole history of the galactic disk. They sample the ages of a star like our sun, the lifetime of a star like our sun. And they also have a range of densities and ages, as you can see, that makes them very suitable to try to study what is the effect of environment and time on the frequency of planets. So, what have we found? So what we have found with Kepler now, our first result from the Kepler cluster study, is we have found 2 mini-Neptune planets. Mini-Neptune meaning about 3 times the size of the Earth. orbiting around two stars similar to our sun inside of the 1 billion year old star cluster. Okay? So we have found two of those planets that are among the most common around field stars as well. Remember Dimitar showed you the Neptune-sized planets are very frequent? And of course, this is exactly how they look, right? We are so unfortunate, perhaps, that in our solar system we have no analogs, we have no representatives of this category of planets that are so frequent around other stars. We have no planets in our solar system between the size of Earth and Neptune, where these mini Neptunes fall. So this is, of course, an honest interpretation. But that is what we found, okay? And these are the first transiting planets in a cluster, and also the smallest cluster planets known to date. So what can we learn from this result? What can we learn from this discovery? What can we learn about the frequency and the nature of planets in clusters? Well, we found these two, and these are, as I said, belongs to this category of the most common planets around field stars. And so what we can do is we can rely on the wealth of information we have from Kepler, all the statistics that Dimitar alluded to. And we can make a prediction saying, if we assume that the frequency of planets is the same inside the star cluster as outside, we can use the information we have about the stars we know about in the cluster, the stars that we searched for planets around, and we can make a prediction of how many planets should we have found in the cluster with Kepler if the frequency was the same as in the field. And the answer to that is that we should have found 4 plus minus 2 of planets of all sizes. So our 2 planets that we found, in fact, tells us that it is consistent, okay? There is no inconsistency between the frequency of planets in clusters and outside of clusters. If we ask specifically to the size of the mini Neptune planets, our prediction is that we should have found 2 like we did. And the fact that we didn't find any smaller planets like Earths and super-Earths, or larger planets like Jupiter or larger, is also consistent with the prediction that such planets we should have found 1 plus minus 1 or 0.6 plus minus 0.6. So our result here, our first result from Kepler of finding planets in a star cluster, tells us that, as the title of our paper, that we have the same frequency of planets inside and outside of star clusters. Now, the other thing that we could look at is that the sizes of our planets and their orbital periods, the time it takes them to go around their stars, are in fact also the most common sizes and the most common orbital periods, suggesting to us that perhaps the nature of the planets in clusters is similar to those outside of clusters. Okay? Now, it is of course now interesting to sort of turn back time and try and see if we can understand how does this cluster look at the time that these 2 planets formed. Okay? And we can do that because we have information about the stars in the cluster. And we can then use certain things, laws of astrophysics to go back and say that this cluster, at the time that these planets formed, contained about 6,000 stars, and at least a handful or 2 of these very massive stars. And if we assume certain reasonable things about the density, we can also say that these 6,000 stars or more were very close together, with an average separation of about 1/10 of a light year. So about 40 or 50 times as close as between the sun and our nearest neighbor. So, to wrap it up, it's probably premature for us to say whether the environment does not affect the frequency and the nature of planets and planetary systems inside of clusters. But what we can say is that it appears that planets, and even small planets, the formation of planets is robust against these very extreme environments with encounters and supernova explosions and radiation in these clusters. Okay? And so perhaps, as this background is supposed to indicate, perhaps planets are like weeds, right? We find them where we expect to, but apparently they can also survive in the most hostile of places. And with that, I will end.
Nice work, Soren. So my job is to tell you about the future, what we think the next steps will be, what our agenda is towards Dimitar's dream of detecting remotely signs, evidence of life on other planets. And this is a mission, the next mission called TESS, the Transiting Exoplanet Survey Satellite. It's headquartered here in Cambridge. The principal investigator is George Ricker at MIT. And the science office is here at the CFA as well as at MIT. And TESS will focus on finding the nearest transiting planets, especially rocky planets that have a surface, and very especially rocky planets at the right distances from their stars, that the temperature could be right for water to be liquid on their surface. And as you've heard, Kepler had a different goal. It had a different purpose, which it succeeded magnificently in doing, finding out how common Earth-like planets are. And now we know they are very common. We want to understand them in detail. We really want to study their atmospheres, because that's the part that we can see and sense remotely. So you saw the launch of Kepler, and you saw the one field of view that Kepler stares at. It's about 100 square degrees. That's a tiny fraction of the entire sky. The entire sky has 400 times more area, and Kepler stared at that one field of view continuously over all 4 years. And it found lots of interesting planets, but did it find the most interesting ones? Would that be pretty surprising if all the most interesting ones were in that one tiny area of the sky? No, the next step is to look at the entire sky. So here's the slide that Dimitar showed you. The Kepler pointing is to a small area of the sky, and because it is at a small area of the sky, in order to get enough targets, it had to go quite faint. So the stars that it studied are mostly far away and look dim. And what we want to do is look in the region around the sun. We'd like to look at things that are 5 times or 10 times closer, which means they'll be 25 times or 100 times brighter. That will allow us to do the follow-up observations to characterize them and maybe even study their atmospheres. So here is a movie that I hope will work that shows you how the TESS mission will do it. It's a satellite that is in orbit around the Earth and the Moon. It's in a lunar resonant orbit. It has 4 lenses inside of the sunshade here that are very wide angle. They look at large areas on the sky so that we can cover most of the sky in a reasonable time. The mission is nominally 2 years long. Oh, you turned it off here. And you see that there are 4 camera fields stacked up from the ecliptic, that's the path of the sun, up to the north ecliptic pole. It stares at that region for almost a month, 27 days, and then it moves on to a second region. 13 of these to cover the entire northern hemisphere, one after another, 1 month after another, until it has the full coverage of the north, looking at almost the entire sky. You'll see there's a little bit of gaps here. In fact, we're having quite a discussion, a mission of how to fill in the gaps by making the mission just a little bit longer, if NASA will let us. And after the northern hemisphere is covered, then the spacecraft reorients and does something very similar in the southern sky. A 2-year nominal mission. We're building the spacecraft so that it will last longer than 2 years. And if everything goes successfully, we will be able to continue for another 2 years after that and go back and look at the most interesting regions that we have identified to get longer time coverage, to get extra observations on the most interesting targets. So I thought I'd tell you a little bit about the genealogy of TESS, how it all came about. Because already 7 years ago, we were thinking about what would be the next step. And George Ricker was an X-ray astronomer. And 7 years ago, we got to talking about what you should do after Kepler. Where did we do this? Did we do it at MIT or here at the CFA? No, we did it in Chicago. Why did we do it in Chicago? Well, it's because we were and still are both trophy husbands, and we take our wives to the annual meeting of the American Medical Association, where they're both famous doctors. And we had lots of time to work on the internet in our hotel rooms and then talk to each other afterwards about ideas. And that's where we first got the idea to repurpose a mission that George was the principal investigator on, HEDI 2, an X-ray mission, that had a little optical camera, 1-inch diameter lens on it. And NASA was retiring the X-ray part of the HEDI 2 mission, and we found an opportunity to propose a mission that would repurpose that optical camera and stare at bright stars and maybe find 1 or 2 hot Jupiters. And we submitted a proposal to NASA for a mission of opportunity for $10 million, and it was not selected. Thank God it wasn't selected, because then we would have had to do it. But we had a bright idea. Well, maybe a naive idea. We didn't need NASA. We'd get some rich people to give us $20 million to do a space mission. So we tried that for a year. It was restructured as a privately funded small mission. We talked to all the people that we could get in to see. The only success that we had was with Google. We gave a presentation at Google, a tech talk at Google, George and I did. And we got something. We got a T-shirt. Oh, these are coveted T-shirts. It says, "I gave a tech talk at Google." But that wasn't the end of the story. About a month later, $250,000 arrived. And so we used that to study the mission. Thank you, Google. But that didn't get anywhere. $250,000 was not enough. And then an opportunity came along for a small Explorer mission, a full NASA mission. And we worked hard to put together a proposal for that. And we actually got selected, 1 out of 3 astrophysics missions that were selected for further study. But the GEMS mission won that selection. The cap on that was $104 million. You see how much more it costs to do things? Well, when you're NASA, or maybe when you understand how it actually works. And, it's a good thing we didn't get selected for that mission, because the selecting official said you underestimated your costs. The official was right, because we really thought it was going to cost $130 million, but we squeezed it down to $104 in order to stay under the cap. GEMS was viewed as being affordable, but guess what? It got canceled when it had cost overruns. And thank goodness we didn't have to do that mission, because it was only going to look at a part of the sky for 1/10 of each low Earth orbit, 10 minutes out of 90 minutes. And what we learned from Kepler was how important it is to have almost continuous light curves. So you see the shape of the transit events, so you see other transiting planets in the same system, and you can tell them apart because you don't miss any of them. So when another opportunity came along in 2010 for a full Explorer mission with a $200 million cap, which seemed like a lot of money, just barely enough, because we wanted to go to a new orbit that would allow almost continuous coverage, just like Kepler had showed us was very important. And you can learn about that orbit by going to YouTube, because the rest of the video that I started is on YouTube, and it shows you this really special orbit, a lunar resonant orbit that allows us to do that. And this proposal was selected for Phase A and then was selected for formulation last April. So we're going ahead with it. And what Kepler does is provide bright nearby. They're bright because they're nearby, the nearest examples of different transiting planets, the best for follow-up work. So here's the size, 1 times the radius of the Earth. The Kepler planets are in blue, and they're down at the bottom because they tend to be fainter than 12th magnitude. Now that's pretty faint. 6th magnitude is the visual limit. The red planets that we anticipate, we predict TESS will be able to discover, are much brighter because they're much closer. They're 30 to 100 times brighter than the Kepler targets. And it'll be these targets up here, the small ones, the bright ones, that will be the best candidates for the follow-up studies. The yield that we predict for the TESS mission is something like 300 Earths and super-Earths. Again, you see this plot of a histogram, a bar chart of the big planets. Those will be easy because they're so big. The small ones, we won't find so many, even though they're very numerous in reality, because we're running into the limitations of the sensitivity of the mission. All over the sky. This is a 2-dimensional representation of the whole sky. But to me, the most important, most exciting thing about finding nearby transiting planets is because we can hope to study their atmospheres. Transiting planets give you 2 opportunities to detect their atmospheres and even do spectroscopy of their atmospheres, so you can learn something about the chemical composition of the atmosphere and how hot it is, its temperature, and even something about its weather. This has been done already for giant planets, giant transiting planets, but now we're going to do it for much smaller planets, much more challenging problem. And the case that I want to focus on is when the planet goes in front of the star, and the atmosphere, this shell of an atmosphere at the edge of the planet, is blocking some of the light. Well, how it blocks the light depends on the wavelength and whether you have strong absorption from molecules in the atmosphere. The size of the atmosphere and the amount of light it blocks during its transit, how deep the transit is, depends on what wavelength you're looking at. So in a sense, you see the radiation from the star transmitted through the planet's atmosphere, and that's how you can characterize what the chemical composition and the temperature of the atmosphere might be. Now, the best target for this kind of work so far, as we push down towards things the size of the Earth, was actually discovered by the MERTH project, which looks at the smallest and coolest stars. And it can do it from the ground with this array of 8 telescopes in the north and a similar array just coming into operation in the south. The smallest stars give you a bigger signal because the same size planet blocks a larger fraction of the small star's area. So you can see smaller stars even though you have to look through the Earth's atmosphere. And it's looking at cool stars. That's also important because the orbit where the temperature is right for water to be liquid, the habitable zone, is much closer in. The periods, instead of being a year, are more like 2 weeks or a month. So this makes it easier, more likely that you're going to find a transiting example. A project led by David Charbonneau here. And there has been one discovery in 4 years of observations, but oh my, what an important discovery. So Gliese 1214 has a transiting planet discovered from the ground on Mount Hopkins in Arizona. It's pretty big, 2.7 times the size of the Earth, and it's quite a bit more massive than the Earth. And it's a really short period, so even though the parent star is quite cool, it's really hot on the surface. Okay, we're not talking about a habitable planet here, but it's the smallest one that we've been able to study the atmosphere of so far. It might even be a water-rich planet, like the one that Dimitar was showing you on one of his slides. And here's what the spectrum has shown so far. So here is that same kind of plot. You saw the theoretical models from Dimitar. Now you're seeing the models overplotted with the observations, the individual points. And if this object has a extended atmosphere of hydrogen and helium, light gases, like the sun, the same composition as the sun, then the spectrum should have these bumps and wiggles. And the observations don't show those bumps and wiggles. So it doesn't have an extended hydrogen and helium atmosphere. Well, if it's mostly a water planet, then the atmosphere is much more compact and you don't get the same number of bumps and wiggles as a function of wavelength. And the observations, boy, it's kind of suggestive. Maybe there's a feature in here, but it's really at the limit of the observations. Well, there is a paper just been submitted that has followed up on this, looking at that small region in here, and now expanding it out for Gliese 1214. And now you see the points are clustered much tighter together. Here they are, the individual points. No longer is there any question about the hydrogen and helium. It even looks like the water atmosphere is ruled out. Well, here's a carbon dioxide. Let's see, which is carbon dioxide is this one here. Is that consistent or not? So with a lot of orbits on the Hubble Space Telescope, it's been possible to push the analysis of this atmosphere to new limits. We want to do this kind of work now with even smaller planets, things that are rocky. We'd love to do it for things at the right distance for water to be liquid. So that's what TESS is all about in my mind, identifying the best targets for this kind of work. For follow-up with the next generation of space telescopes, the James Webb Space Telescope, launched maybe in 2018 or a little after, or the gigantic telescopes. The Europeans have the ELT. The Americans have two, but I'm only going to show you the one that we're involved in here, the Giant Magellan Telescope. I'm not going to show you the one about the Californians. And with these instruments, we can characterize the planets, the candidates found by TESS. So this is our dream. By 2020, we will have used TESS to identify the nearest small planets. Soon after, we will start using a big new spectrometer, the next generation spectrometer after HARPS that Dimitar was touching, on the Giant Magellan Telescope, which is going to cost close to $1 billion, and half of that money is committed so far. And that'll confirm the orbits and show which ones are rocky because they have the right mass and radius to have the density of rock, just like the Earth. And soon after, or about the same time, we'll be using JWST from space and these gigantic telescopes from the ground to characterize the chemical composition of a handful, 1 or 2 or 4, who knows how many, but the very best targets will get the most attention. And then by when? Here's the real challenge. Finding evidence that life has polluted an atmosphere enough so that we can detect it remotely. Thank you.